All right, I want to go over example E2.1, and I want to do just the first part. I'll do the first part now, and then I'll follow with the second. I want to find the electric field at point A due to these two charges, and I want to use the vector method of doing it. So I want to use the electric field is equal to KQ over R cubed times R vector. That's what I want to. That's the form I want to use. All right. So the first thing we need to do is we need to write down the display or the locations of the charges and the location of A in vector form. So let's call this Q1 and this Q2. So R1, the location of Q1, I'm going to write it as a vector. Right, so it's on the x-axis at location minus d over 2. If this is d, and assume that the origin is at the center, centered between these two charges, then I know that this is going to be at a negative d over 2. Okay, what about R2? So this charge is at a positive d over 2, right? Here's my origin. This is d, so it's located in the center. So this must be equal to d over 2, 0, 0. And the location of A is d away from Q, and then add a half to that. So that's equal to negative 3/2, 0, 0, times d. Okay, so now if I think about what this R means, it's the distance between my charge and the place where I want to determine the field. So, so I want the vector that goes from Q out to A. And so I can just see that that's going to equal D, right? If I want to go this way, and it's going to be a negative D because it's going to point away from Q and towards A, and our coordinate system looks like this. So to the right is positive x. All right, so let's see if we can do this with vectors to see if that's what we get. So what we want to do is we want to take the vector that represents the location of A and subtract the vector that represents the location of Q1, and we want to see if we get negative D. So RA, okay, so let's just draw this for a second. If I have my origin here and I have Q here, this is going to be R1. Right, that's the vector that represents the location of Q. And now if I have A over here, then this vector is going to represent the location of A. So if I want to subtract them, let's call subtracting them RA1, so that's the vector from Q to A, then we're going to say that's equal to RA minus R1. And we'll say that's equal to, if I plug in what RA is, I get a negative 3/2 D, and then minus a negative d over 2. And so RA1 equals a negative 3/2 minus a negative half d, right? So a negative 3/2, that just becomes a plus. So what I get is 2/2, which is just a negative d. So let's write that out. So here, this is a negative 3/2, and so minus a negative 1/2, right, all times d. So that becomes a negative 3/2, and then a negative of a negative is a positive, plus 1/2 times d. And so a negative 3/2 plus a half becomes a negative 2/2 d, which is a negative d. That's where that comes from. Okay, so now what about RA? Let's see. So RA1 is equal to RA minus R1, or I'm sorry, R8, this should be 2. RA2 is RA minus RA2, R2. So we have negative 3/2 D, 0, 0, minus D over 2, 0, 0. So for RA2, and so RA2 means this distance, right? So what we did is we're taking the location of A and subtracting the location of Q2. So we should get this vector. So I would assume that we're going to get 2D here. Let's see what we get. So negative 3/2 D minus D over 2, would give me negative 4/2 d. So 4d over 2. And so 4 over 2, this is, and this is a negative. So this gives me 2d, 0, 0, just as I had expected. Okay, so now I've got my displacement vectors that represent Q1 to A and Q2 to A. Now I want to find my electric field. So E at A is going to equal E at A due to 1, charge 1, plus E at A due to charge 2, because of the superposition principle. Okay, so EA, if I use my formula here, I'm going to have KQ over, and now R cubed, the length of this vector from here to here, right, I know it's D, so I'm going to say over D cubed times a negative D, 0, 0, plus K, this is going to be a negative Q over, and now the R here, right, is going to be 2D, right? That's what I would get here. So 2D cubed, and now this is going to say 2D, 0, 0. Okay, so EA equals, these are vectors, equals, so now I can factor out, I have a KQ over D cubed. I can factor that out of both of them, and here I'm left with a minus D for this one, and here I have minus, because of the negative here, and I have 2D there, and I also have over 8. See, this one has a D cubed and this one has a 2D cubed, so 2 cubed is 8. So when I factored out the D cubed, I still had the 8 over here, so I'm going to have, this is going to be over 8, and then I'm going to have 0, 0 here. So EA equals KQ over D cubed. Now I can factor out a D out of here, and so I'm left with a minus 1 minus a quarter, 0, 0. And so I can cancel, this becomes squared, and so EA equals KQ over D squared, and then this minus 1 minus a quarter is minus 5/4. And let's check our answer here. Oh, that's right, we forgot up here. That's right, over here on this negative 4/2, I forgot to keep my negative, so I still have a negative here and I have a negative here. So that means this negative and this negative we add. So I have, so this is a negative D and then plus a quarter. So this becomes plus. And so now instead of 5/4, I have 3/4. Negative 3/4. And so if I factor that out, EA equals KQ over D squared and 3/4 here, and then I have a minus 1, 0, 0. So that's what my electric field looks like. And does that make sense? Right? If I imagine what my electric field is here, my electric field is going to be stronger due to the positive charge because I'm closer. Right? If I look at this field here, if I look at this, let's look at this one, this R cubed, the smaller the R is, the bigger my E is. So I'm going to expect a pretty big electric field here like that. And now for what about this one? This one, the field is going to be pointing towards the charge, and since this is further away, I'm going to have a smaller E field here. So when I add these two together, I'm going to have a net positive, or I'm sorry, I'm going to have a net negative charge going to the left due to these two charges. And so that makes sense when I think about what I did quantitatively, and then if I think about it qualitatively.